Okay guys, this will be a tutorial video on how to use the Halbach magnet array simulation GUI software to simulate the in-plane B-field results that you measured using hop probe during the hop probe measurement experiment. Okay, so I'm going to go through how to run the program, how to actually set it up properly, how to visualize the experimental and theoretical results side by side, and in the end probably troubleshoot on some of the most common problems you may encounter during the use of the program. Okay, so now let's start. First, to run the program, I think the best way and probably error-free way is to run the source code directly in MATLAB. Right? You don't have to have any prior experience in MATLAB to actually do it properly, because this is really easy. First, you need to make sure that hold on one second. First you need to make sure that the source code, there are two of them, all right? This is the first thing you have to pay attention to. There's a .m file. This is the MATLAB script file, or the source code, the actual source code file. And then there's a .fig file, the visual layout of the GUI. You have to make sure that both of them are included in the same folder somewhere in your computer. And preferably, you should also place your experimental data files in the same folder, all right? Just to avoid some nasty problems when you're trying to load the experimental data, right? And then open your MATLAB, or if you don't have it, you go to one of the campus computer, use your EWS desktop, or just borrow from a friend who has. Okay. Open the MATLAB window, and you can type in the file name. Oh, sorry. After you open it, you need to make sure the working directory here is exactly the same folder containing the source code. All right, this is very important. If you run the source code from a different location, the GUI will still pop up, but I don't think the software will function properly, because the folder may not be defined in the working path in the MATLAB library. Okay, there's some technical details. So make sure the working directory is pointing to the current folder containing the source code. You can type in the path here, or you can actually, direct your way to that particular folder just by pressing the arrows. Okay, pretty much like Files Explorer. Okay, and once you have that, once your working directory is appropriate, you can actually see a list of files contained in that folder currently in the current folder window, and then you can type in the file name of the source code or of the GUI, directly press enter and it'll run, or you can actually right click on the file and just press run. Okay, that's how you start it. And then you can see that this is the basic layout of the GUI. The leftmost column here contains all the necessary inputs for the theoretical simulation. So this is where I will start. First, the scanning grid and magnetic array setup. You have to complete basically these two sections to specify completely a multi-pole magnet array configuration. All right. So let's work with a concrete example. This is a typical quadruple configuration of magnets. Try to open it outside. As you can see here, 4 magnets aligning in a cross shape, symmetric about the origin, and evenly spaced from the origin. And the size of the grid, as you can, I'm not sure if you can read it clearly, is first the shape of the grid is square, and the size is actually 2 by 2, so spanning from -1 to +1 in both directions. Okay, so to actually make this simulation software register exactly this kind of setup, you need to first specify the step size of the scanning grid in both directions. Right, as you can see, I've specified 2 numbers here. You can actually specify just 1 or 2 separated by comma or white space to actually indicate or tell the program the step size your probe took during the actual experiment, okay, in either x and y or y. And then the second row specified the number of steps. Again, depending on your setup, it could be just a single number in both directions, or different values in either directions, again separated by common white space. All right, so it's basically the setting here defines if you have a square grid. If you use a single number, that'll be a square grid. If you use two numbers, then it'll come up, the simulation grid will come out to be rectangular. Pretty reasonable and simple. All right, and then the third row, as indicated by the arrow here in the configuration diagram, specify the initial position of the hop row. All right, let me hover my mouse over this, and this brings up. Oh, by the way, if you hover your mouse over a certain item in the software, then I think for a couple of seconds, and then the tooltip for that particular section or for that particular parameter will actually pop up. All right. So as you can see here from the tooltip, this is actually the initial position of the hop probe, or where your probe started during the actual measurement. All right. I think for most typical setup, most groups should, well, almost, if not all, should start their probe with the from the top left corner of the scanning grid. All right. So just like the arrow indicates here, and so that's why I specify the default value as -1 and +1, and which is the top left corner. Okay. It doesn't have to be at the top left corner at all. You can actually change this to say -1, -1, which is the bottom left corner here, and instead, correspondingly, change the step size to be pointing in positive direction in both, pointing positive in both directions. All right, positive x and positive y. So specifying the bottom left corner with positive step size is exactly the same as specifying the top right corner, 1, 1 here, with a negative step size. All right. So you can use either. You can use any one of those four corners here of your grid, and then change the sign of your step size accordingly, and then it'll set up the same exact square grid or a rectangular grid. Okay. And the fourth one and the fifth one here are kind of like a minor tweaks of the calculation result. So you can, if you're not sure what they're doing, then you can just leave them at their default value, 0 and 1, and it doesn't affect the final result that much. This one may affect your result a lot. Just like the name suggests, probe height, this value here, first it should be a single numeric value, either positive or negative or 0. And ideally much smaller than the range of the scanning grid. The number here actually specifies or defines the height, the actual height of the probe, elevated from the plane of the magnetic array. Okay, so if you think about it, the default value 0 assumes that the probe is actually in plane, exactly in plane with the magnetic array, which is definitely not the case during your experiment. Right, your probe is actually somewhat higher than the actual setup and than the actual magnetic array. So you may want to correct for that possible elevation, probe elevation here, by specifying some numbers for the z position of the probe, so to speak. All right. So I'm going to put 0.1 here. I'm actually going to show what it does once we have the theoretical result in display. Okay. An m value is just like an overall proportional constant multiplied to the b value, to the b field value. So you can leave it as 1. Unless you want to do a quantitative, an exact comparison between experiment and theory, then you have to worry about the exact value of m. Okay. Otherwise, just leave it as 1. Okay. And then the magnetic array setup, this is the real deal. You have to specify the orientation and the coordinate of every single magnet in your setup. Okay, so trying to replicate the setup here in this diagram, you have to specify the x and y coordinates of each magnet. So that'll be 0, negative 0.5, 0, and then negative 0.5, negative 0. And you have to specify the angle each magnet makes with the positive x direction. Right? So this is an angle of 0 degree. And this will be 90 degrees, counting positive counterclockwise as the positive direction for angle. Right? And this is 180. Wait. Hold on. 0 positive, so this is 90, and this is 0, 180, and this is 270. Okay? So just remember, the angle is measured from positive x-axis, and the positive direction is by the same convention used in any mathematical textbook, any kind of book that deals with Cartesian coordinate system. Right? Counterclockwise is positive, and counting from positive x-axis. And also make sure that you type in the angles in degrees. Right? Do not type in radians. It doesn't support radians. Okay, if you type in y, I think, yeah, it'll come out as not a number in your input, and in turn actually makes the whole calculation invalid, if not generating an actual error message. Okay, so make sure the angles are in degrees, which is also reminded to you in the tooltip. All right. So once you think you're finished with this setup here, specifying every single magnet and also finish specifying the dimension of the scanning grid, then you can actually calculate. I will explain these two things later. You can actually press the calculate button, and it'll pop up a message of successful calculation, and then you can plot the theoretical result. Okay? So that's pretty much it with the theoretical calculation. And then you can see that by the limit of the axis, this is a square grid of size 2 by 2. So if you have a rectangular grid like this, then calculate again, and then you can see that the display, the window of display is still squared in shape, and sorry, there's no easy way to change the actual shape, but you can see the range of display in y-axis is no longer negative 1 to 1, but actually negative 2 to 1. All right. It's not negative 1 to 2 because we're specifying our starting position to be this point. So your y is actually going like this. So if I specify the initial position to be negative 1 in y, like this, bottom left corner, do it again, and then you can see that the range of y actually starts from negative 1 to positive 2. All right. So be careful with that. Make sure that you understand the meaning of those numbers here, and it helps that you actually draw the geometrical shape with the limiting values of the axis with your settings first. Okay. So what you can do is that you can actually specify just a single magnet here, or just specify some random values here. Press calculate and show it, and see if the range of display and the shape of the display is correct or matches your experimental setup. Okay, so that's it. Let me bring it back to the original setting. Oh, just remember, if you changed anything here in scanning grid or in magnetic array setup, if you change any setting here, you have to press calculate again to update the result. Okay. Now, what's next? Okay. Now comes the, well, I will explain the plotting section probably in the end, because most of the functions here are self-evident. You can just play around with it and just press the button and you see what it does. I don't think I need to waste your time of explaining in details what each of those settings is for, right? And just try it out and you'll see. I'd like to point out one thing though, the use of the data mask. Sorry, I have to save it. The data mask is an arbitrary setting that specifies a square region around each magnet to be ignored during the actual plot. All right. So this value has to be between 0 and 1. So the bigger the setting, the bigger the blank region, the blank squares you see covering each magnet. And this is there. This parameter is there because the B field values close to each magnet, like these points here, here, and here, will tend to be extremely big, as you can probably imagine, and we want to avoid those regions, because if you include those regions of extreme B values, then you can see the plot will be dominated by those extreme points, right? So then the details of the in-between areas of your setup will actually be blurred or actually overwhelmed. Okay. Once you load the experiment data, then you see that the resolution of your experiment data tends to be much worse, much worse compared to the theoretical simulation. So in order to make some reasonable qualitative comparison even, you have to actually play around with the data mask setting to make sure that you review the minor details in between the magnets and avoid the extreme values. Okay, and also here I'm going to explain what this number does, the probe height. Okay, this is the default setting, probe height 0. If I update it, then you can see that this is pretty much what you can imagine the B field like, exactly in plane with the magnet array, right? Extreme value here and here and also here and here, since I'm showing the X component. Only these 2 points will show significant value in B field. Okay. Similarly for Y, only 2 points along the Y-axis. These two magnets will generate significant value. Or in other words, the extreme B values at these 2 points will actually overwhelm all the other details in the plot. All right. So this is definitely not a feature observable in your experimental data, because we're assuming in simulation that each of the magnet is point-like, and occupying exactly this point, or exactly only one single point in the coordinate system, which is definitely not true. Each magnet has its finite size and finite height, and the probe is not exactly in plane with the magnet, so you probably have to manually raise it by changing this number here and show it again. See, this is like 0.2 unit above the plane of the magnet array, and you can see apparently there's a huge difference in the shape of the magnetic field, because we're actually moving away from the extreme region, and you tend to see more details and more irregularities because we're no longer in plane. So the setup doesn't have the inversion symmetry about the XY plane. Okay, so you can see more asymmetry developing in the result. Okay, so you can actually play around with the setting here, and just remember, if you want to make a really good qualitative comparison between simulation and experiment, then you have to specify the step size, number of steps, initial position, probe height, and X and Y coordinates exactly according to your experimental setup. All right, that means you have to use whatever the actual number of steps you're using, and especially for these values, this step size, initial position, probe height, X coordinates, and Y coordinates, you have to make sure they're all in the same unit, and preferably in the actual unit of the movement and the dimension of your of the foam and of your actual experiment. Right? If you recall that the actual experiment, well, actually, the magnet mapper program that you used for data collection in the experiment uses inches as the as the unit for measuring distance and coordinates. So you probably have to specify the coordinates of each magnet in inches as well, specify the height of the probe in inches, initial position in inches, and step size in inches. Okay, they could also all be in centimeters, or even be in the weird unit of so-called stepper size unit, the weird unit used in the magnet mapper software during the experiment, if you still recall. One one stepper size unit is equal to 1/200th of an inch, right? So basically a nice number that you specify when you're using the software. Okay, so just keep in mind that you have to make sure these values are in the same unit and probably reflect exactly the dimension of your experimental setup. Okay, so that's pretty much it about the simulation section of the GUI. If you're happy with the simulation result and you want to save it, if you want to record it in a TXT file, in a data file, then you can actually press the save button and it'll pop for confirmation. Click yes to save, and then you can see in the same folder as the software, the program actually saves 4 files: bx underline theory, by underline theory, xgrid, and ygrid. These files are just the numerical matrix for the b values of each component. And the xgrid and ygrid file are basically 2 grid files. If you're not sure what grid file is, you can try to Google the help file on this command, meshgrid command, and MATLAB has a pretty detailed and very instructive help file on how to use this command and what it actually means. Okay, but you can see it's basically a data matrix of the same dimension as the b values, specifying the x coordinates of every single point in your scanning grid. This is for x grid, and for y grid, it's the specifying all the y coordinates in the scanning grid. Okay, so that's what grid file actually mean, and which will be used pretty soon in the experimental loading section. Okay, so now onto the experimental part of the GUI software. To load the experimental data properly, you have to specify, at a minimum, the first 2 rows here. Specify the file name of your experimental data, including the extension. Okay. This brings me back to the very first thing I mentioned when I opened the software, that you have to place everything in the same folder, so that you don't have to type in the full path for this file here. You can place the experimental data file in a different folder, but then you have to specify the exact path, right? The full path like this, starting from the drive label, and it's just a really big hassle and a pain in the ass to actually worry about. All right, so just remember to place everything of interest in the same folder. Okay, and one more thing to make sure that your experimental data is loaded properly. All right, let me show you a run example. Hold on. Oh, so it actually works. Okay, great. This is perfect. This is perfect. All right, anyway, a possible error may occur when you're loading experimental data directly from the original data file, which looks like this. All right, this is what a typical experimental data looks like that you collect using the magnet mapper software. Okay. Apart from having the actual data matrix, you have an extra row on top of things specifying the x coordinate, initial and final position of the x coordinates, and extra column specifying the starting and final y coordinates, and also probably some header lines, 1 row or maybe 2 rows specifying the informational details of the scan, like the date, time, number of steps in each direction, the starting coordinates of x, starting coordinates of y, and things like that, and probably the name of the file, something like that. All right. These text-based information, these rows and this last columns, are undesirable to be used with the GUI software. All right. I tried it here, and it seems to be working with the GUI software, but you may have some error loading experimental data file like this in its very original raw format. All right, so if you have a problem with that, if you have any kind of error when you're loading the experimental data, then the best way to do is to erase all those text-based information from your data file. Okay, erase this column and these two rows, the first two rows. Basically, transform your data file into something like this. Okay, nothing, no text information whatsoever, just the pure data matrix, numerical matrix. Okay, for both x and y, and then you can save it as any kind of scientific data format, as with well-defined delimiters. So Excel workbook is fine. The old version of Excel is fine. Let me see. TXT file is definitely fine, and then CSV file is also fine, and spreadsheet is also fine. Things like that. So basically anything that looks like a DAT file, a .dat file. Okay. All right. So that's it. Once you have that, and once you change the format in both of the raw data file, and then you can actually load the experimental data. You don't have to specify the X and Y grid file. Just input the first two rows should be enough. All right, load it successfully. And then if you click plot again, then it'll actually show you the updated display with both simulation and experiment. If you clear the simulation and plot again, then of course there will be only the experiment that will actually be shown. Okay, so that's pretty much it. However, you may want to use these two settings here as well, because as you can see, the program, the software, assumes a 2x2 square grid for your experimental data if you do not specify these two files, right, from -1 to +1. So basically it assumes the same default setting. It copied the same default setting from the scanning grid setup here and apply it to your actual data grid, which may well not be the case for your experimental setup. Like I said, your actual scanning grid may be rectangular, and the size may well be beyond 2x2, maybe like 12 by 14 centimeter squared. Okay, so to reflect the actual experimental setup properly, what you can do is you can define your own grid file manually like this. Again, go to the help file for this command to see how to actually define this kind of data matrix quickly. All right. Or a lazy way of doing things is that you specify the settings here properly, reflecting exactly, like I said, exactly your experimental setup. And once you're done with the calculation, save the file as txt, save the data as txt file, and then use the theoretical grid file as your experimental grid. All right. So basically transferring the grid setting here onto your experimental data. It should work. Come on. Okay. So you can see there's a minor change. Well, actually, there's no there's no factual change here because I'm basically copying. These two are not actual experimental data. These two are actually theoretical results coming from exactly the same calculation here. So that's why you don't see much change here, probably apart from the scale of the calculation. But if you specify the value here according to your actual setup and then apply it and then copy the setting over here, then the range here will update itself to match more reasonably with your experimental setup. Okay, so that's how you actually compare them. Compare the simulation results and the experimental results on a more equal footing. Okay, so that's it with the experimental loading, with the simulation. And if you want to save the current display, all you need to do is to specify the file format for your figure and just save it. It'll save again, as you probably guessed, a file with a proper name, a very easy to recognize name, easily recognizable name, file name, with the correct type that you specify here. Okay, so this is a 3D contour _by plot, of both simulation and experiment. If you have only experiment like this, save it, then it'll only save the right window and with a different file name, right? 3D contour by underscore experiment. Okay, so the saving feature should be very considerate to you and should encompass all possible scenarios of your possible selection of parameters here. You don't have to worry about getting confused or getting lost with the saved files. You can easily tell what the saved figure is about, which each of the figure is about, just by looking at its file name. Okay, and for those of you who have prior experience with MATLAB, I recommend saving the display as .fig file. This is the default. What am I trying to say? Okay, this is the default figure format for MATLAB figures, only openable in MATLAB. So if you save it as fig, saved. Let me see where it is. There we go. Then you can actually open it in MATLAB window, and for further editing, then you can actually fine tweak the color setting, the contour setting, and then the perspective of the 3D maps, of the 3D plot. So basically, do a fine tweak, further fine tweaks of the display in MATLAB. All right. So that's pretty much it. What else? Oh, one last thing. All right. One thing I've been ignoring up to now. These two settings here. Okay. Just like the name suggests, and the two tips indicate, the invert button, invert box of these two inversion box actually manually invert the all of the coordinates of the corresponding section. So this one inverts all of the x coordinates, and this one inverts all the y coordinates. And that includes all the y coordinates of the whole scanning grid, of your simulation grid. All right, it doesn't affect the experiment. Simulation grid and all the coordinates here in your magnet array setup. So let me show you what it does. If I invert y, calculate again, you can see the message actually changes to remind you that some kind of inversion is in place here. And plot again, you can see apparently the red peaks and blue peaks seems to be switching places. Okay, pretty obvious. If you invert x and I plot x component, then you can see that it basically switched the polarity of your calculation. The reason these two options are included here is because the magnet mapper software you used in the experiment has a very awkward definition for the positive y direction. Our most common sense definition for positive y would be like going from going like this, going upwards. But in the actual experimental setup, the magnet mapper software assumes downwards as the positive y direction. So this is really awkward, and this may actually introduce a hidden minus sign in your calculated result, or actually in one of the components of your calculated result. This hidden minus sign may also be caused by an inappropriate orientation of the probe. Right? Remember, the Hubble probe is a vector probe, so it does have a sense of positive direction for measurement results. Okay, so if you flip the probe by 180 degrees, or if you flip the axial probe horizontally, or if you flip the transversal probe by 180 degrees, then you may accidentally introduce a negative sign in your data without knowing it. Right? So to compensate for that possible error, as you can see, which is not so clear right now, but to compensate for a possible scenario like this, as you can see here, there's a apparent sign error between simulation and experiment. Blue here, red here, red here, blue here. To compensate for this possible, disagreement or flip in sign between experiment and simulation, I've included these two options So you can actually play around with them. You may actually turn one or both on, like this or like this, to actually bring your simulation and experimental result in agreement. All right. So you can see apparently there's a sign error here. So if I clear the inversion option for y, then yeah, it corrects for that. Okay. So that's what these two options are for. Okay, and I think that concludes all the necessary information you need to properly use the software. If you have any further question, you can try to consult the README file for this software here in the same folder in the server of the course. All right, and the file name should be very informational. All right, the newest and most useful README file, so you know where to look for. And I think the NA file. Let me open it. And I'm sorry, this is an old version, so I'm not going to bother you with the details of it. It basically covered everything I've said here. Probably something I forgot to mention as well, and also some useful troubleshooting tips and useful tips on actually using the software efficiently in this file here. All right. So if you have any further questions, make sure to direct your attention to this file, or ask your TA for help. Okay. And that's it. Ciao.